We're going to start today's lecture off on ionization energy. And I know from past experience, this is a little bit more of a complicated idea. And it's something that definitely shows up on quizzes and exams and the AP exam. So it's something you want to work at to make sure you can kind of commit it to memory. So what is ionization energy? It is the energy, keyword, required, not involved, but required, to remove an electron from an atom. So many times we call it like I1 for the first, and I2 for the second, and so on. And just as a general trend, and we're going to go over some slides here in just a moment. Our little periodic table. Generally going in this direction, it is increasing. And rhetorically, I would ask, why would you say the ionization energy is increasing going from left to right? And if you said Zeph, you are 100% right. It's just like a knee-jerk reaction. Going from left to right, it is Zeph. In other words, as that magnet strength, think about it, in the nucleus, is increasing going across, the energy required to remove a negative electron from this magnet is going to be more difficult. It's going to be requiring more energy to take it away. That makes sense. Now, the thought process going up or down, ionization energy, which should it be? And this may not be as obvious, but it's actually going in this direction. So you may be focusing on the protons. When you're talking up and down, the conversation you want to be having is shells, the size of the atom. As the electron gets further and further away from the nucleus, it's easier to remove. So again, increasing going up. It's closer to that positive nucleus. There's less shielding involved. So it's easier to easier to attract that electron to the nucleus as opposed to further away. Okay, let me bounce over to a slide. And this gets a little bit complicated. We're going to focus on lithium, beryllium, and then boron on through here. And notice what you would see, based on what we were just talking about, ionization energy should increase going across. And it says that specifically right there. So as we're going from lithium to boron, you may not be able to read that. I think I can read it. It's 899. But then notice that boron is less, which goes against what we were just talking about. And then you can look at carbon. Okay, it's going up. It's going up for nitrogen, but then it goes down again. That doesn't make sense. So we have two discontinuities in there. And we can see that same trend happening in the next row down with sodium, magnesium. And then if we just focus on the P block moving across, we kind of see a similar idea kind of going around over here. But it's really pronounced over here. And that's what we're going to kind of take a look at. And so right now I'm just kind of leaving you with that thought as to why this is happening. We're going to explain this more in just a moment. This chart here, I'll focus on this one before we bounce over to making a chart on our notes. Going from left to right, you got sodium, magnesium, and across the row. Notice, again, as far as the energy required to take one electron away, it is going up generally. You got this little thing going on here. So I was like, what's going on there? But generally it is increasing going up. So the general idea again is Zeph. So I want to leave it at that as far as that conversation. What I really want to focus on, and this is one of the things that people struggle with, is moving from left to right. Why is this happening? First ionization energy is only 500-ish. Second ionization, it's like 10 times more. Why? I'm not going to answer yet. Magnesium, you have this value and then this one, and then a huge jump. Why? Same thing for aluminum. 1, 2, 3. We're just looking at these trends. They're all increasing, I get that. But when you take this next electron away, as they're kind of indicating here, it's a very large jump. And we're trying to figure out why that is. So let's bounce back over to our notes. And see if we can figure this out. So first thing I'm going to show here, and I can't show both at the same time, but we'll talk about it. We could see for the ionization energy, for sodium, taking that one electron away, it was 500 or so, whatever. But then taking the next electron away was very difficult, or it required a lot of energy. And the reason for that is because that next electron is in another energy shell closer to the nucleus, less shielding, which we talked about before. So the first one, okay, it's on the outside shell, but anything less into the interior shell is very, very difficult to remove because of the lack of shielding that this one has, but these guys do not have. And I'm talking about electrons. Magnesium can lose 2 relatively easily, but to lose the third electron from magnesium, so the third electron to take away, very difficult because again, less shielding. Aluminum can lose 3 relatively easily. It will not lose the fourth because again, it's in the shell closer to the nucleus and it has less shielding. And that's the way it'll work. Okay. Let's come on back to the discontinuities. I'm going to draw a little chart here. Pull this down a little bit. And we'll just have some arbitrary numbers in here. These are ionization energies or just energy. And then the elements we're going to list here are beryllium, boron, carbon, nitrogen, oxygen, and fluorine. We'll stick with those guys. And if we just focus on looking at removing electrons, this is kind of how it'll go. And these are just kind of arbitrary numbers. To remove an electron from beryllium, okay? To remove an electron from boron, it actually requires less energy, even though Zeph should tell us that it should go up. It goes down, as we saw in that chart. We'll talk more in just a moment. And then we kind of see the trend go the way we expect it should. Carbon goes up, nitrogen goes up, but oxygen falls. It goes down for oxygen. And then looking at fluorine, the trend goes back to the way it should be. So I kind of draw these out, connect the dots. This is what we see. And the reason for it is, again, if we take a look at 1s, 2s, 2p. When we're looking at, we'll do beryllium. So bring over here, beryllium has a total of 4 electrons. So if we're doing beryllium, to take an electron away from beryllium, okay, fine, it takes some energy and boop, there it goes, whatever, all on its own. But for boron, that electron with 5 is hanging out in a higher energy level. So taking this electron away is relatively easier than taking the electron away from beryllium because it's at a higher energy level. And then subsequent, looking at carbon, nitrogen, but then look at oxygen. Because this orbital already has an electron in it, you have a little bit more repulsion. So this electron for oxygen is relatively easier to take away than it was for the previous nitrogen. And then the trend just kind of continues along because of, again, Zeph moving from left to right. They're pulled in stronger. But because of the couple of discontinuities, the first one found at a higher energy level, and then oxygen's, because it's already filled with one electron, it actually goes down. So the whole Zeph thing in general is absolutely true. But there's a little bit of a discontinuity, a little bit of a hiccup going from left to right for some of these guys. All right, we'll call that the end of this lecture, and we'll pick it up from there.